Okay, good morning. Today we'll be undertaking L7.1, which is an activity describing color vision and color filters. First of all, we're going to step back to look at refraction. We have learned a simplified version of refraction through prisms, and we are going to make it a trifle more complicated right now. Before, I guess, we did the truth, but not the whole truth, and we're going to do a bit closer to the whole truth this time around. We actually set up a prism. And we have white light coming in and striking, moving from air to glass and back to air. Our ray strikes the interface between the air and the glass. We can draw a normal at that point. And what happens is, instead of passing through unchanged, it is refracted. It is bent. And the rule that we've learned is that it's bent towards the normal, 1/3 away from the straight line path, 1/3 of the angle of incidence. And that is, in fact, a simplification. We've already discussed this. So we move through the glass. Again, we strike an interface. This time it's a glass-air interface. The ray of light is again refracted. This time it bends away from the normal on the far side of the interface. And it bends away by 1/2 of the angle of incidence. And as a result of that, the prism acts as if it was the thin edge of a converging lens. It bends light down towards where the focus would be on a converging lens. This is a simplified rule. Okay? Now, in the 1600s, a gentleman named Isaac Newton ran away from the Black Plague in London, spent the summer at the farm, actually spent 2 years at the back of the farm, and he studied exactly this effect. He took a prism, sat in a dark little room, made a pinhole in a blind, and looked at the ray of light progressing through the prism. And what he saw is he did see this bending, but he also saw something else. The beam of light split up. It was dispersed, was his phrase, and it split out into different colors. What I've drawn here is kind of the average. If you look up very closely to it, you will find that at each of these interfaces where refraction takes place, red refracts less than average. So the red light is bent less. Next comes orange, next comes yellow, next comes green. That somewhere around the average is green. Finally, blue and purple bend more than average. And what we get out here is we get the classical spectrum out, and it would be written red, orange, yellow, green, blue, indigo, violet by tradition, because that's the way Isaac Newton first wrote it back in the 1600s. We're now seeing some different effects producing different colors. And in fact, this is called the visual spectrum, or the optical spectrum, or the rainbow. And in fact, if you don't use glass prisms, but you use round water droplets, very many of them, you will get a rainbow. Anyway, so what we are going to do is we're going to look today at color filters. We need to have a nice bright spectrum to start with. Now, we're not going to use this technique to produce a spectrum. This technique kind of produces lousy spectrums. Unless you've got millions of small raindrops, you don't get a strong spectrum. So what we're going to do is instead we're going to use a more modern piece of technology called a holographic grating. It has 10,000 lines per centimeter on this particular piece. And when I tape it over the overhead, you'll see faint smears of color on it. And what you're seeing here is you're seeing millions of different spectra that are in no ways aligned, just as we did when we looked at the pinhole and made it bigger and bigger and bigger, and our images got blurrier and blurrier and blurrier, and they weren't all aligned with one another. That's what we're seeing right here. So what we're going to do is we're going to cut down the amount of light. So we want to get a nice bright standing spectrum. So I'll create an optical slit using 2 pieces of cardboard like this. Now, notice what I've done here. I've created an optical slit in the middle of the overhead. But look over here on the side. Both sides have spectra. There's something reversed about this spectra. It's not quite right. If you look at a prism spectra, red light is bent the least. Blue light is bent the most. Here the reverse happens, and that's due to the geometry of the interference gratings. And should you choose to take Physics 112, they'll go into that in considerable detail. Now, all the colors are there. This is like playing a piano where you play all 88 keys in a row. And 3 of the keys are hooked up to an electric guitar amplifier. So 3 of the notes come out screamingly loud, and the other 85 are quite quiet. When we see the optical spectrum here, there are millions of colors. But red, green, and blue come out louder than any other single color. And that's actually an important clue as to how our eyes are designed. This device over here you're all familiar with. Okay, so what I got here is I've got the slit. You can see the slit right here on this side. And I have the spectrum, and you can see the spectrum over here. And what I'm going to do now is we're going to add some filters and try and figure out what's going on here. Okay, if you look at the very top here, the top of the slit, here's the top of the slit. You can actually see the red filter here. The rest of the slit, which has no color on it. So over here we see all the colors of the spectrum. What do we see here? Red, a little bit of orange. So what does a red filter do?
It only allows the red light through.
Red filter. The red filter only allows the red light through. That's all it does. Okay, now knowing that, red filters absorb everything but red, then we would expect blue filters to absorb everything but blue. Is that correct? Okay. There's a little bit of green getting through. Yes, it's not perfect. These filters are not ideal. If you look over here on the red filter, a little bit of orange and green actually got through. If we look at the blue filter, a little bit of green got through. But it really blocked out this side, and the red filter really, for sure, blocked out that side. So they're not perfect, but it looks like we've got a grip on what the filters do. Green is in the center of the spectrum. Okay, here we blocked the right-hand side, here we blocked the left-hand side, and here we blocked everything but the center. And notice that we got these little snippets here that give us the complete spectrum for reference over here. So it looks like colored filters block everything but the color they are. Red filters block everything but red. Blue blocks everything but blue. Green blocks everything but green. Okay, so let's have a look at these things. Okay, so what color do we have up here? Well, first of all, what color is the filter? It's a cyan filter. Cyan is kind of a turquoise color. And what is cyan letting through? It's letting through blue and green.
Blue and green makes them cyan, so it'll let both of those colors through.
Okay, so blue and green together are adding to give us cyan, so it lets 2 colors through. And it's blocked out all what? Red. Magenta. Magenta lets what through? Magenta is allowing red and blue through. Magenta leaves out green. I remember that because magenta's got G for green in it. Okay, so magenta blocks out most of the green. And again, it's not perfect. Some of the green is getting through. But it's taken out the center of our spectrum here. And our last filter is yellow in that sequence. And this is a pretty orangish yellow. I think gives you the idea. And the yellow blocks off the left-hand side of the spectrum that we see here. Okay, so the complementary colors also work by passing certain chunks of the spectrum. But these filters act by passing 2 pieces of the spectrum, not 1 piece, and blocking the third. So RGB pass everything but RGB, magenta, cyan, and yellow, but those colors are in fact mixtures of RGB. So they're letting two parts of the spectrum through. We can use either RGB or CMY.